Yeah, good point.
So, perfect segue into a little bit of an architecture discussion. Um, the simplest architecture involves employing a single core packet broker, uh, for our solution. And here, all observed data, whether it's taps, fans, tunnels, they're all terminated on the core packet broker. Remember that each tap will require 2 ports on the packet broker since we're capturing the full duplex conversation. In this example, we're looking at our Vision X platform, which, as Tim mentioned, is ideal for those higher speed implementations. So what does it look like when we scale that single tier architecture? Well, bottom line, it involves adding additional cards as we add more segments that will be observed or need more tool ports. But obviously, there's a limit to how far we can scale with this architecture on any given platform. So what happens when we're looking at a larger deployment? Well, enter the multi-tier architecture. Here, edge packet brokers are employed to aggregate data. Because these are significantly less expensive platforms than those with all the intelligence, it's very economical to terminate taps here. It also preserves ports on the core packet broker for greater scale, as you can see. Now, this would introduce more complexity in getting the data to the tools without a key enabling feature we call multi-hop. This feature takes care of all the intermediate hops between the infrastructure components for you. You simply select the source data ports and connect them to the tool ports without care to where they physically reside. As you'll see in a couple slides, this is not limited to a 2-tier architecture like we're seeing here. So how does this scale? Well, it's pretty simple. Scaling horizontally, is much more efficient with efficient uses, again, on the core packet broker of ports on that core packet broker. So let's take a look at a little bit more interesting solution, just to get an idea for scale. In this example, we've employed a 3-tier architecture. So the first tier is row-based aggregation, and this is actually a real example. In this case, floor 1 already existed, and I know it's small, but what you'll notice there is a lot of, in green and blue, 1 and 10 gig observation points or taps, including even copper that was in place initially. They had a need to build out 40 and 100 gig connectivity, and so they added a new floor. And all of the existing deployment was reusable simply by adding a middle tier aggregation layer, which also aggregates flow from the new 40 and 100 gig infrastructure. Now, again, critical to this deployment is the multi-hop feature. The user doesn't have to care about the packet routing that has to occur between the tiers to get data from a tap to a tool. You want more detail about how routing decisions are made, please reach out to your RSM or SE and they'd be happy to discuss. Some other notes, notice also where some of our sizing calculations come into play. Here we need to ensure that appropriate bandwidth is given to interconnects to carry the max aggregation load from one hop to the next. And you can see that in the red and purple links in the middle. Notice also that port utilization on the core packet broker remains low, allowing for significantly greater scale to be achieved.
Yeah, this nicely solves what looks like a pretty complex and sort of broad architecture. And those edge aggregators, as you mentioned, they keep it cost effective as well on a sort of a per port basis.
All right, so we're going to actually switch